Welcome back to Engineering Edge. In this episode, we are setting up a new project in Robot Structural Analysis Professional. You will learn how to define units, understand coordinate systems, and configure basic modeling preferences, all before we begin drawing or analyzing anything. Let's begin by opening the Robot Structural Analysis Professional software. Click on New to start a new project. You will see a list of structural model types to choose from, including the building design, the load takedown building design, frame 3D design, shell design, truss 3D design, and many more. We will go through each of these in later videos, but for now, let's choose building design for this lesson. Once the main software interface opens up, just like we showed in episode 1, let's start by saving our projects right away. So we go to File, we save. Let's call this one episode 2_setup and save it to the desktop. So we are saving it to the desktop. We save it episode. Episode 2_setup. We save it to the desktop. So let's save it. This first save is very important because the software may crash unexpectedly and you don't want to lose your work. Okay, after saving the project, let's define our preferred units, materials, design codes, analysis types, and meshing options. So to do this, we'll go to the tools menu, then we'll go to job preference. This is where you can change your unit, your type of reinforcement depending on the country that you choose, the design codes you'll be using, the structural analysis, how you want it to be performed. So for the unit, depending on your location or country, you may be using either the metric system or the imperial unit system. For this tutorial, we'll stick with the metric system, and the dimension will go with whatever we have here, the one that is already in the software, so that we can make things easier. Okay, so let's move on. Always, the advice we usually give to beginners is always use a consistent unit system across all your projects. It keeps your results easier to interpret and helps avoid mistakes. So if you are using the metric system, go with the metric system. If you are using the imperial, do imperial. Don't mix the two together. It can be confusing sometimes. So that is it for the unit. After you've set up, now you have to understand your coordinate systems. So in robots, we have the two main coordinate systems. We have the global coordinate system, and then we have the local coordinate system. So let's now explore the global coordinate system. So just as you can see here, let me draw a square around it. Just like you can see here, this is basically showing you the global coordinate system. The x direction as you are seeing here is the horizontal direction. Normally the y direction is the depth, and then the z is the vertical axis. So you have to know that is very important. As this is a brief explanation of the global coordinate system. Now let's move on to the local coordinate system. This usually is very good. You can see it clearly with your members. Let's check out this diagram. So as you can see, let's open this diagram and check it out. Okay, it shows both 2D and then 3D views. The local axis for the 3D, as you can see, the local axis for the 2D, the local axis runs along the length of the member from start node A to end node B. So you have start node A to end node. Start node. This is the A, and then this is the B. So that is where you start and where you go is normally the direction of the X. And then the local y-axis is perpendicular. It's when you are showing it in 2D, it's usually perpendicular to the X. So this is the Y. So this is the Y. So that is it. It's perpendicular to the X. In 3D view, as you are seeing here, you also have the local z-axis, which is usually pointing to the top. So like you are seeing here, this is the X, which is usually pointing to the top. The X is still the same. The X is still starting from where your node, your first node is to your second node. So that's the A and B. The Y is perpendicular to it, and then the X is the vertical direction. So for this particular diagram can help you understand the local coordinate system for members. But for vertical members, somebody will ask, how would the vertical member behave? The same thing. For vertical members, the local x-axis is vertical because you've turned it in a vertical position. You see that your x-axis now becomes in the local, it becomes, the x-axis is now the vertical, and then the y and the z adjust accordingly. Okay, so now let's draw a simple frame structure and look at how the local coordinate system shows up on the elements. So let me close this one. Close this one. So let's draw it here in the X. We are just going to do a 3 meter by 3 meter one. That's for the Y. So let's do 3 meter. Another no, go 3 meter by 3 meter. And in the X, I mean, we are using the story, so it's already 3 meter, but I'm going to do some change there as well. So let me go to the plan. Let me delete the story. We are not doing story for now. We'll understand the story later in our subsequent videos. Yes. So now let me go back to the grid system, and then the y-axis, I'm also going to make it 3 meters. The set axis, I'm going to make it 3 meters. I'm going to change the numbering to values so that we see it that way. Okay, so if you come to the view, the 3D view, you see the 3 meter there, and then the X and the Y also there. So plan. Let's just create a simple beam. Let me first. Sorry. Let me come here and then take it to the 3 meter top. Create my beams. So I'm starting from the node 1 for this beam is starting from 1 and is going to grade 2 this place. Other one is starting from 2, then we'll draw. Let's finish drawing. We can understand it later. Now this is what we have. We can show it in 3D view. We can have it nicely. Let me draw the columns as well. Let's use this UC here. Let me delete them. I'll come back to that. Let's go back to the plan. Let's do this UC. Let's choose down here. Okay, so now let's show it in 3D. You can see it here. It's clearly drawn. So now let's show the coordinate system for the local coordinate system so that we can understand this thing very well. So we go to view. You can go to view here. You go to display. Then under display, you go to the model, and then you can show the local system. The local systems here, you can show it here. Then go to apply. So you can clearly see for this particular member, we started from the grade line 1 up to the grade line 2. And just like we read earlier, the local x-axis runs along the length of the member. So the x-axis, which is the blue, as you can see here, is running along the length of the member in the horizontal direction, whilst the y is usually perpendicular to the x. So you can see the y in this direction, and then the z is in the vertical direction. So that is what I'm talking about. But if you have this vertical member here, you can see that now the x, which is the blue here, is pointing in the vertical direction. Then the y will be perpendicular to it in this direction here, and then the z in the other direction, just like it's showing. So this is how the coordinate system works. So for plates, let's draw a plate so that we can understand plate 2 as well. Let's draw a simple plate. Let me go to panels here. Then let me go to a floor. Let me just use this one here. I draw a simple plate here. Now if I'm showing the coordinate system for the plates, you can see what is happening here. For plates or panels, the local coordinate system usually follows the global coordinate system, making load application easier. So you can see the global coordinate system you have here is basically the same as what you are having for the plates here. So we have to note that it's very, very important, so that you don't confuse yourself. So that is it for the plate as well. Now let's move on. So with questions, the question is, why does the global and the local coordinate system matter in the design and analysis of structures? One of the most important things to do in analysis of a structure is load application. And in robot structural analysis, loads are applied by default in the global coordinate system, not the local one, unless you want to change it manually yourself, which for beginners, I would advise against that. It's not recommended. But if you want to do that, you can always go to edit. You can go to edit here, and then you can go to edit, another edit. The drop down, there's another edit there. You go to transformation of the coordinate system. You can do those changes here. So that is it here. You can do your changes here. That is it. Okay. So for the load application. So now let's look at some few points that make these two system important in our structural design and analysis. Let's start with the global coordinate system. The global coordinate system provides a universal frame of reference for your building. It ensures consistent placement, load direction, and interpretation, and is best for gravity, wind, and seismic load application. Okay, now what about the local coordinate system? For the local coordinate system, it helps apply load relative to member geometry. Example, self-weight of a member of a sloped beam. You can easily apply you can apply load of a for a slope beam using the local coordinate system. Needed for understanding of internal forces. After your design, you need to check your moment in your X, your moment in the Y and the Z direction, and it usually goes with the local coordinate system, just as the shear as well in both the Y and the Z direction. And it's also useful for checking deformation, torsion, and bending behavior of structural members. So in summary, the global coordinate system helps you build the structure in 3D space, while the local coordinate system helps you understand how each element behaves under loads. So now that we are done with the coordinate system, let's look at the modeling preferences and display settings. So for you to do that, you can go back to the tools, but this time around not the job preference but preferences, and then you can choose the language you want to use. If it's Great Britain, whatever language you want to use for your software, you can choose it here. The original settings, the working language, the printouts, whatever. Then you can use your view. Depending on your graphics card that you are using, you can increase the display acceleration. It becomes more clearer. The 3D becomes more nicer. If your graphics card is not that good, you can reduce it so that your software doesn't lag when you are using it. Then you can come to the desktop setting. If you want to change from blue, you can change it from blue to maybe dark green. You can change it to dark, whatever color you want to use, but I want to go with a deep blue, so I'll maintain it. Your printout composition, your advanced, whatever you want to do here, you can easily do it. So and you have to remember, a clean personalized interface will help reduce errors and make modeling more efficient. So it's important you do all this setup before you start your modeling, your analysis, your modeling and analysis. So for today, so that is how you probably set up a new project in robot structural analysis, from defining your unit system and understanding coordinate system to adjusting modeling preferences. Your workspace is now optimized and ready for productivity. In the next video, we will begin creating structural grids and geometry, starting with drawing columns, beams, and slabs. You don't want to miss it, so hit subscribe and turn on notifications. If you found this video helpful, drop a like, share with fellow engineers, and let me know in the comments what part you would like more detail on. Thanks for watching and see you in the next one. Bye bye.